afternoon session of day 3 of this ongoing 5-day Gyan course. For this afternoon first lecture, that is 10th lecture of this Gyan course, Professor Naoki Shinohara will be delivering a talk on theory and technology of amplifier for WPT, that is part 2 based on microwave tubes. I invite you to start the talk.
So, welcome back again at the afternoon session of the GN course day 3. So, I mentioned in this morning, today, mainly I would like to explain the transmitter technology. And in this morning, I've already explained the amplifier technology with semiconductors. But so it's a very hopeful technology now and near future semiconductor technology. Year by year, technology or characteristic of the semiconductor is advancing, but unfortunately, it's very, very expensive. If we have a very small amount of the budget, but if we promise we will develop, for example, a 100 watt WPT demonstration or kilowatt demonstration, unfortunately, we cannot adopt the semiconductor. In this case, I recommend you to use microwave tube. It's very cheap and very good efficiency devices. So, as I explain again, we need these characteristics as a microwave transmitter: high efficiency, high power, and phase controllable and cheap, not expensive. So, in this viewpoint, I recommend you to use the microwave tubes: magnetron, klystron, sometimes gyrotron, etc., vacuum tubes. Of course, historically, vacuum tube was developed for the a lot of circuit, for example, audio, TV, etc. And later, new solid-state device was born. And now, almost all vacuum devices changed to the solid-state. But in the microwave frequency technology, we can still use the vacuum device, vacuum tubes. So some of you watched the Hollywood movie, Tom Cruise, Top Gun Maverick. This is a very famous and similar word in the Top Gun Maverick. So end of the microwave tube is inevitable. So your kind is heating to extension. But Tom Cruise replied, maybe so, but not today. This is a very important reply. Not today. Of course, in near future, I don't know. But just now, I recommend you to use microwave tube. So from here, briefly, I would like to introduce an overview of the microwave tubes. These are three famous microwave tubes. Just now, we can use it. So most interesting device is a magnetron. So in your room or in your house, there is a microwave oven to heat up your food. In all microwave oven, there is a magnetron. It's very cheap device and high power, high efficiency, very good microwave tubes. And so a large amount of the microwave tube are provided in your home, in the world. And TWT, traveling wave tube, is adopted for the wireless, satellite wireless communication systems. And this is a very good device, but a little bit expensive. And frequency is limited for the satellite communication. It is recently. And last one is klystron. And Crestron was applied for the broadcasting wireless communication about 50 years ago or 60 years ago. Both TWT and Crestron as a microwave amplifier. We can use it. But recently, instead of the Crestron, now we have a MIMO wireless transmitter for wireless communication, and all wireless communication system we adopted the semiconductor. But so, for example, in my campus of Kyoto University, second campus, there are a lot of Crestron to heat up the plasmas for atomic fusion. It can generate megawatt or very huge power. So this magnetron is applied for the atomic fusion research recently. And different between three systems is how to generate or how to amplify the microwave. In the magnetron, we use only a structure of the resonator in vacuum, and electric field and magnetic field are used. And electron from the source is controlled by the E field cross H field. Usually we call it E cross H drift. So it's very simple structure. When we add the high voltage, electron is transmitted from the source, and this propagating electron is controlled by the E cross H drift mainly. And these two microwave tube, TWT, Crestron, they use an electron gun. So first of all, they generate the electron from the gun. And this electron beam will be modulated and up to the microwave frequency. And at last, they got over 100 watt power or sometimes megawatt power. So a big difference between these three microwave tube is how to generate the microwave magnetron use only a E cross H drift. And these two types, they adopt the electron gun, electron beam system. So these two microwave tubes are a little bit expensive compared to the magnetron. Magnetron is a very, very cheap device. And this is a hyper microwave WPT demonstrations in history. So of course in 60s and 70s and 80s, they adopted microwave tube as a microwave source. And recently, sometimes use the magnetron there. And I pick up a major demonstration of the radiative WPT here, but please check it. There are a lot of magnetron as a microwave tube still now. So if we have enough budget to carry out the demonstration of the radiative WPT, a lot of people still choose magnetron. So Tom Cruise explain again, not now. And this is some example of the WPT demonstration with microwave tubes. So historically, as I mentioned again and again in this course, William Bragg chose a microwave magnetron for the demonstration. And at that time, he realized that about 70% conversion efficiency with magnetrons. And I showed you the Kyoto University's world first WPT demonstration in space. And at that time, here is a waveguide, and inside box, my boss adopted the magnetron, especially cooker type magnetron. Very, very cheap device. He launched into the space, and he succeeded in the space experiment in 80s. It is named Minix. And in Canada, I mentioned before, in this course, they carried out the very interesting world first WPT-aided airplane experiment named SHARP in 1987. At that time, they adopted here, you can see they adopted the parabolic antenna plus magnetron systems. And recently in Kyoto University, we have some collaborative research with a car company, Japanese car company. Unfortunately, not Toyota, Nissan, and Subaru or the other group had collaborative research with us. And to charge the electrical vehicle, we don't adopt the inductive wireless charger. At that time, we adopted wireless power via microwave. And at that time, we transmitted, for example, 6.6 kilovolt, and over the kilowatt microwave was transmitted from the road to the car body. And at that time, we adopted the magnetron for this demonstration. And in the first day, I mentioned this Japanese demonstration with magnetron at a distance of the 500 meters. And not only Japan, but also in US, for example. About 4 years ago, US Army Research Field, they carried out the about 1 kilometer WPT demonstration towards a solar power satellite. And at that time, they adopted a 5 meters parabolic antenna with a pulse magnetron of the approximately 100 kilowatts. And the frequency was expanded about 10 gigahertz. And this experiment was very, very excellent. And they transmitted at first about 100 kilowatts from the transmitter. And at 1 kilometers away, they received about 1.6 kilowatts and to turn on this drive. So recently, this experiment was the largest demonstration of the microwave power transfer. So 5 years ago, they still use magnetron, microwave tube. So magnetron or microwave tube are not old technology. So this is a new technology. And I pick up mainly magnetron because magnetron is the cheapest microwave tubes in the world. And here is a magnetron characteristic and pictures. Inside this box, this is the main part of the magnetron. And here you can see a vacuum chamber inside this area. And this is just a cylinder structure. And from the source, we add about 3,050 kilovolts to burn the electrons. And after propagating the electrons into the vacuum, we add the magnetic field vertically. And from the source to the outside, we add the electric field. So E cross H creates the other force to drive the electron to go to the rotating. And outside of this vacuum area, we add the resonator structure. We make it just at 2.45 gigahertz for the microwave oven. So by this resonator, this rotating electrons are focused some area, and this rotating motion by electron create plus and plus minus at the 2.45 gigahertz. So this is a very simple structure and a simple operation only by the high voltage electric field and magnetic field only. So in your home, I suppose there is one microwave oven in all house. And sometimes we use it pulse radar or wireless power transfer. And magnetron has a very long history, about over 100 years. So about 100 years ago, to 1921, Dr. Hall proposed the first magnetron in US. And this is just a very basic technology of the magnetron, and this was not good efficiency magnetron. So after invention of the magnetron by Hall 100 years ago, a lot of people revised this magnetron. And around the World War II, Raytheon company US update this magnetron, and a lot of magnetron were applied for the radars, for example. And spin-off technology from the magnetron radar. So engineer in Raytheon found microwave power can heat the candy or the chocolate. So in the experiment in the Raytheon for the radar technology, they find microwave can be applied as a heat power. So magnetron, Raytheon invent microwave oven with help of the magnetron technology. And after World War II, Japanese company Panasonic revised the microwave oven, and now we all can use the microwave oven with magnetron. And this is a structure of the magnetron and the operation principle, as I explained now. So here is a cylinder structure by vacuum, and these structure of the resonator. And from the inside to the outside, we add the voltage, and so between these walls, there is an electric field. And vertically, we add the magnetic field, and as a result of the E cross B drift, this is a plasma theory. And this electron moving and rotating through this cylinder, and the electron will be focused as a cloud. And finally, there is a minus area, and there is a no electron means the plus area, and the plus minus microwave will be generated. So this is a simple explanation of the operation of the magnetron. And this is a comparison of the all microwave tube. So as I mentioned, compared to the device, we can generate a very higher power in the microwave tube, and efficiency is very good compared to the microwave devices. And so life is enough for the application, and cost is very, very cheap. So even now, we can choose the magnetron or the microwave tube for the experiment. And this is the cost trend of the magnetron. Year by year, cost becomes very low. And recently, even we have $5, we can buy the 1 kilowatt magnetron. If we have $5 only, we cannot develop the amplifier with the semiconductor of the 1 kilowatt. So cost is 1% or 0.1% of the semiconductor devices. So magnetron is a very, very good device, low cost, high efficiency, and high power. But unfortunately, magnetron itself is an oscillator, not amplifier. Originally, we use the E cross B drift. In the magnetron, microwave will be transmitted. So, and additionally, this is the simple structure. So, spectrum of the frequency from the magnetron is not good. Very wide and dirty spectrum generally. And there are very high spurious noise, and it's most important. Generator, we cannot control the phase and the frequency of the generator. So, but as I explained in this course, we would like to control the beam direction. So, if we choose a parabolic antenna and a mechanical beam controller, of course, we don't mind. But hopefully, we would like to electronical beam forming with a phased array antenna. And for phased array antenna, we need we need to control the phase and the frequency in the transmitter. So first of all, we run a lot of technology from William Brown's paper. And in Kyoto University in 90s, when I started my research as an assistant professor, at first we developed very low noise magnetron by help of the standardized DC power source and the filament cutoff technology. Usually, in your room, magnetron is driven by the half wavelength, high voltage, very cheap power sources. So, unfortunately, by this fluctuation of the power source, magnetron's wave spectrum is very dirty. So, but we found if we stabilize the power source, we can reduce the noise and we can increase the Q of the wave spectrum of the main frequency from the magnetron. And additionally, filament is the source of the electron. And we need this filament to excite the microwave itself because we need an electron. But once filament current on, we get some electron. But we find after the first excitation of the electron by filament, we can cut the filament current. And but without any filament current, we can keep the generation of the microwave in the microwave. We found it. And when we cut off the filament, so there is no heat noise. And as a result, we can separate the noise from the microwave. And after developing this low noise magnetron, we go advanced to develop the phase control magnetron. We adopted two main technologies. PLL feedback loop, it is usually applied for the semiconductor circuit. And the other is injection locking. And this injection locking technology is often applied for the semiconductor circuit. So based on the semiconductor circuit technology, we, Kyoto University, could develop phase and control magnetron. I will explain later. And the original technology of the phase control magnetron were from the William Brown. And this is a low noise magnetron explanation. So this blue line, this is a frequency and a power level. And usually, if you have a spectrum analyzer in your room, please check the wave spectrum of your microwave. This blue line is typical waveform from the microwave. And in this case, we use unstabilized, very simple DC power source of the 3,500 kilovolts, 500 volts. But when we stabilize the DC power source, wave spectrum suddenly becomes very pure. Here you can see this red line. So Q factor of the spectrum becomes very high. So waveform of the magnetron depends on the DC power source stabilization of the fluctuation. We found it. And additionally, we can cut the filament current. So based on these two technology, we find the same cooker type chip magnetron can be applied for the high quality microwave source. And next, we develop phase control magnetron. So as I mentioned, now magnetron is an oscillator. So we, Kyoto University, could develop the very low noise magnetron, and the spectrum becomes lower and the Q factor becomes higher. But still frequency and amplitude changes as the temperature of the magnetron changes. And the phase of magnetron cannot be controlled because magnetron is an oscillator. So in the next step, we add the two technologies, PL feedback and injection locking technology to control the phase and additionally amplitude. And this is a real originally magnetron amplifier, phase control magnetron developed by the William Brown. here you can see magnetron, and she used the same technology, injection locking reference microwave signal to this magnetron, and this waveform of the magnetron is catched by the weak reference signal. This is the injection locking technology. And additionally, he controls the magnetic field mainly here. This is a feedback loop to control the frequency by change of the magnetic field here, magnetic field. So William Brown succeeded in this phase control magnetron, and this system seems to be the amplifier, because here is the input signal as a reference signal, and the output power is a very high power from the magnetron. So it seems to be an amplifier, so William Brown named magnetron amplifier. And the other group is developed in China. They are developing the very similar system, and so they revised this phase control magnetron. But before the Chinese group, we, Kyoto University, has already developed this phase control magnetron. And injection locking is the same. But once I tried to develop exactly the same magnetron amplifier of the William Brown, but we added the external coil to control the magnetic field, but I failed. So I suppose changing range of the magnetic field was not enough in our experiment. So we consider to increase the frequency changing range, not by the magnetic field, but by the changing the electric field voltage control. We propose it, and by change of the voltage source, it's easy to control the frequency widely. So we, Kyoto University, reached this type of phase control magnetron, injection locking plus PL feedback to the electric field, high voltage. So we succeeded in the phase control magnetron. And this is the basic theory, the Alder's equation. And this theory can describe the all circuit technology of the semiconductor amplifier and magnetron both. And catching frequency lock range is calculated from this equation, and it involves the ratio of the output power from the magnetron and the input power of the reference signal. So based on this signal, usually, for example, a magnetron has a 1 kilowatt output power. And if we use a 1 kilowatt reference signal, it's easy to expand the frequency locking range, but there is no meaning. So usually, for example, as a reference signal, we use a 1 watt or a few watts only. So this ratio of the output and input power are very big difference. But it's enough to catch the frequency to the reference signal of the magnetron signal. And after locking frequency, next, this is just a frequency locking range. So next, we have to control the phase, and we have the other Adler's equation to describe the phase difference based on the ratio of the input-output power. And this is the experimental data of the injection locking phenomena. At first, magnetron output is here, and the reference signal is here. And originally, frequency are not the same. But based on the Adler's equation, if the frequency difference enough within the locking range, this magnetron output move to the reference signal, weak reference signal, and at last, this weak reference signal catch the hypermagnetron. This is Adler's equation result, and this is a injection locking phenomena, not only in the microwave tube, but also in the microwave circuit with a semiconductor. And after locking, we control the slightly frequency to control the phase. And as a result, we add the PL feedback to control the phase. And as you know, PL is originally from the semiconductor circuit. And we create the feedback with a voltage controlled oscillator. And we add the comparator with the phase. And as a result of the comparison result of the phase, this feedback moved to the voltage to drive the VCO. And as a result, this phase of the VCO is moved to our desired phase. So we use the same feedback loop in magnetron system. And as a result, we control the anode current by PL feedback, and we control the frequency and the power. And as a result of the injection locking and the PL feedback, here you can see it's very pure spectrum from the magnetron. So this waveform is at first phase difference between two reference signal, original reference signal and the magnetron signal is 0. And when we change the signal of the phase of the reference signal 180 degrees, here you can see we can control the phase difference on the magnetron. And this is a final and the first system of the phase control magnetron. Here is a magnetron, and there are the control feedback circuit, and the reference signal is here. And this could be drive well, and we can develop the phased array only by with magnetrons. And next, we move to to develop the phase and amplitude control magnetron, because when we change the electric field, it means we change the voltage of the electric field, and as a result, we can control the phase and frequency, and simultaneously, power is changed. So, how do we think about this problem? So, at last, we add the control circuit of the magnetic field. As I mentioned today, magnetron microwave is created by E cross H, electric field and magnetic field. So William Brown controls the magnetic field only, and we, Kyoto University, control the electric field only. But frequency and power both can be controlled by the electric field and the magnetic field both. So we combine, and mainly we control the frequency and the phase by change of the electric field, and additionally we control the magnetic field to change the power. So as a result, this double feedback, this is the original phase control magnetron, and we add the amplitude control PL feedback here. And as a result, we can control or we can stabilize the power. For example, when we stabilize the phase, usually if there is no PLL or there is an original Kuka type magnetron, time by time, phase is changed and the power is changed by change of the temperature. And we add the phase control feedback. Phase keeps the same, but unfortunately, the power changes slightly by change of the temperature. And at last, we add the amplitude feedback. So phase keeps the same and the power keeps the same, even when we control the output power of the phase, etc. So this is our Kyoto University goal, phase and amplitude control magnetron, to develop a good phased array antennas. So, this is our first reaching point. But we would like to move to the higher frequency, as I mentioned in this course again and again. This technology mainly based on the Kuka type magnetron, 2.45 gigahertz. And 2.45 gigahertz magnetron is only one device with a very cheap $5 for 1 kilowatt. But if we would like to choose the 5.8 gigahertz magnetron or 10 gigahertz magnetron, etc., unfortunately, there is no Kuka type magnetron in the world. So a little bit expensive, and additionally, characteristic of the magnetron is worse than the Kuka type well-made 2.45 gigahertz magnetron. So we have a collaborated research with Panasonic. Panasonic is one of the biggest companies to develop the magnetron itself. So we ordered to develop the 5.8 gigahertz magnetron to Panasonic, and they did it. But this is data of the magnetron current and frequency changes, and this trend is required to go for the PL feedback. When we change the current increase, frequency increase, and the current decreases, frequency decreases. This trend is very important. But developed 5.8 gigahertz magnetron, we checked it. This trend is not good. And magnetron, each magnetron has a different trend. For example, this red line. So when we increase the current, frequency decreases uncontrollably. So if we have these magnetron with characteristic, unfortunately, we cannot develop a very good PL feedback loop. So we consider how to control this very strange magnetron at the 5.8 gigahertz. So one of my young staff proposed this new type PLL locking loop, PLL feedback, not to the electric field, not to the magnetic field, PLL feedback to the input signal here. And as a result, we do not control the electric field and magnetic field itself, and we control only the reference signal here. And so it means this feedback loop does not depend on the change characteristic of the magnetron frequency. So we propose this new feedback loop, and as a result, we can catch the phase of this very strange 5.8 gigahertz magnetron. So as a result, if we have a lot of very strange magnetron, we can control the phase and additionally amplitude. And it's very stable phase control magnetron. And this is as a result, phase is very stable, and when we control the power, for example. So this is one very good reaching point of the 5.8 gigahertz magnetron. And this is a very interesting movie of the phased array antenna with a 5.8 gigahertz magnetron. Here you can see this is a 4 phase control magnetron at 5.8 gigahertz. Stop. And now we change the direction of the beam, and here is a receiver. And based on this simulation, we control this direction of the power beam, and here you can see we can control the beam direction only by the magnetron. So this is a very cheap phased array with a very high power. Totally, we transmitted over 1 kilowatt. So this is a very interesting technology, I think so. And this is my final point. So next, so my young colleagues developed the Swift magnetron. About 20 years ago, after success of the development of the phase control magnetron, I tried to develop the Swift magnetron. And to develop the swift magnetron, we must know the frequency response of the magnetron, like a VCO, etc. If frequency response of the oscillator or the magnetron is very poor, even if we at the PLL control, we cannot control the phase and amplitude for the information very high speed. So at that time, frequency response of the Kuka type magnetron was about 1 megawatt only, about 20 years ago. I've checked it. And so at that time, so if we transmit, for example, DVD information or the other, we need at least 100 megahertz or gigahertz, giga PPS speed. So I thought at that time, we cannot magnetron, we cannot use the magnetron as a swift source. But my young staff suddenly found we can control the phase and amplitude with enough speed to modulate the information on the magnetron. So this is a movie. Just a moment. Just a moment. I need a sound. いけてるいけてる。あれ？Sorry, it's very small sound. Please see. Please read this substructure. So this is our developed real codeless TV. There is no power source, power line, and there is no internet connection. There is no line on this TV. This information and the power are transmitted from the outside. Secret is here. So in this case, my colleagues use microwave itself, and he adds the PL feedback and injection locking rate, etc. And he controls the modulation of the microwave from the magnetron, and he adds the information of the DVD on the modulated magnetron microwave. This is the power source of the magnetron, and turn on the TV. The power is transmitted from the magnetron, and DVD information is also transmitted to the magnetron itself. This is real swift system. There is no power divider or etc. But to drive TV itself, we need a very high power, so rectenna is very, very huge. It's unfortunate, but this is just a demonstration to drive the TV. If we have a good gallium nitride or the other, we can reduce the size of the rectifier, I think so. So this is our current final reaching point of the developing magnetron. So I think today I introduced technology with semiconductor and microwave tube. And William Brown has reached already 54% efficiency from the electricity to the electricity in this lab experiment. And this experiment, William Brown adopted magnetron. And of course, now we can adopt the semiconductor and phase array, etc. But unfortunately, if now we choose semiconductor devices, we cannot read the record of the William Brown, unfortunately. So, again, I'd like to recommend you to use microwave tube if you don't have enough budget, and if you need very high power and high efficiency. So it's not an old technology, I think. It's a very future technology, I think so. So harmonization of the circuit and semiconductor and microwave tube is welcome, I think so. So that's all my today's talk. Thank you so much.
Thank you very much, sir, for this wonderful session of afternoon. Is there any query from the participants?
Yeah.
Sir, will it be the same if we use it outside the energy chamber?
Sorry?
Will it be the same if you use outside the energy chamber?
Outside of the energy? What do you mean?
The experiment we are doing inside that chamber.
That entire thing you have kept inside the anechoic chamber.
Now, so
chamber.
if we transmit over 1 kilowatt, so it's easy to understand. It's like a microwave oven, and it's very dangerous system.
Yes.
So of course, in the anechoic chamber, it's very safe circumstance, and we can demonstrate this experiment. But if we get the permission from the government, not only in Japan but also India, so for example, Myrax airplane experiment or the other experiment, if we get the permission from the government and we must keep the safety, we can demonstrate this hyper microwave outside. But now, unfortunately, now we need a permission.
Will it give same result?
Yeah, inside in anechoic chamber and outside, of course, a little bit circumstances are different. For example, ground plane effect, or sometimes, about 30 years ago, when I was a PhD student, I carried out the beaming type WPT experiment outside. And at that time, I carried out this experiment in shiny day, but additionally rainy day, etc. But as I mentioned sometime in this course, microwave frequency is the most suitable frequency without any attenuation by rain or etc. So we have some effect by rain or the other outside parameter, but it's very good experiment, for example. But so mainly, so ground reflection is one problem to check the beam form by the transmitting antenna. So I recommend you to carry out the experiment in the anechoic chamber for journal paper. But if we would like to expand the application of the microwave, in the next step, we must carry out this demonstration or experiment outside.
Thank you, sir.
For short 10 minutes. After that, the tutorial session will be started.
And tomorrow, I'll give the receiver technology, maybe. So, thank you so much. Yes, sir.